Your brain has the incredible ability to learn and infer new algorithms, something that current AI systems struggle to replicate. I'll walk you through an example algorithm which your brain executes so seamlessly you aren't even aware of it. While the algorithm isn't complex, it showcases the human brain's ability to program itself by learning new algorithms and illustrates the scope of programs your brain can execute and the instruction set it must use. Many of our frustrations with AI stem from its limitations compared to the incredible flexibility of the human brain. Let's dive into the mechanics of your brain and see how this knowledge can help advance the next generation of AI. I'm Charles Simon, longtime AI researcher, software developer, and manager. In addition to AI work, I've developed software for several neurological test instruments and neural simulators, and, along the way, learned a lot about the capabilities and limitations of biological neurons and how your brain must work to do the things it does. I founded the Future AI Society to pursue these ideas, and we're in the process of writing all aspects of this process in the open source Brain Simulator 3, and I invite you to participate. To understand human behavior and improve AI, it's essential to understand the basics and observe the simple everyday actions that shape our lives. Unlike the rapid top-down evolution of AI, which often focuses on complex data and algorithms like playing chess or writing a YouTube script, human behavior is rooted in fundamental and often subconscious abilities, many of which we learned as children. By examining these, we can uncover the deeper patterns that govern our intelligence and interactions. In this video, I'll present a problem which you can solve easily and show how your brain likely solves it. But don't click away when you see how simple the example is. The insight here is the algorithm your brain uses, what kind of programming your brain is capable of, and how AI could improve if it could do this too. So here's a question I was asked by a member. If your brain has learned historical facts, how do you know which occurred first? As an example, which came first, the Norman Conquest or the Magna Carta? I'll give you a hint. The Magna Carta was signed in 1215 and the Norman invasion was in 1066. Now, it's an easy question. But how do you know? In your brain, how can you compare 1066 and 1215 and conclude that 1215 is larger and therefore the Norman invasion came first, or conversely, that the Magna Carta came later? Before getting into the details, why did I choose this algorithm as an example? First, it seems really simple, but I'll show you how things are often more complex than they appear. I know you must have learned this algorithm. The fact that your brain can learn algorithms is a key takeaway. And you learned this algorithm so well, you aren't even aware of it when you use it. And it's so fast you can answer in a fraction of a second. On the other hand, a computer can do this nearly 1 billion times faster. But this is just one example of many algorithms you've learned, and I'd like you to think and suggest others. So here's an outline of the algorithm your brain must use to let you answer the question of which is larger, 1066 or 1215. I'll go through it quickly because you may have never thought that you needed an algorithm at all. Then I'll circle back with more details about how your brain must do this. Let's imagine a function compare two numbers, a and b. A and b are equivalent to pointers to the first digit of each number. Now, if number A has more digits, return that A is larger. If B has more digits, return that B is larger. Now we enter a loop. If the digit pointed to by A is greater than the digit pointed to by B, then return A is larger, or the other way around. Then move the A and B pointers to their next digit positions. If there are no more digits, return A and B are equal, and then go back to repeat the loop. As a final note, potentially cache the result. There are variations on this theme which would yield the desired result, but conceptually the algorithm is more or less defined by our decimal number system. The question is, since you've learned this algorithm, can your brain learn any algorithm? What are the limits to the algorithmic complexity? No one knows. But if we crack how the brain learns and stores algorithms, we'll know more about the brain and how we could enable similar capabilities in our AIs. Looking into the details reveals a lot about your brain. There is no possibility that individual neurons or synapses can represent numbers like these. There must be a sequence of digits in some sort of symbolic notation. What about the greater than relationship for individual digits? Clearly in your brain you know the relationship for any pair of digits, and you probably learned this at an early age from some input like this.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Interestingly, now greater than can be defined as comes later in the sequence. This means that in your brain, numbers don't need any mathematical or numerical meaning whatsoever. You can just as easily compare the words cat with dog using a similar algorithm because you know the sequence of letters in the alphabet the same way you know the sequence of digits in counting to 10. Now, what do I mean by return anyway? This meaning is well known for a computer program. In your brain, though, it likely means add a relationship between the given arguments. In this algorithm, there are only 3 return values: A equals B, A is greater than B, B is greater than A. So your brain can add a relationship between the nodes representing the two numbers, indicating which came first, or perhaps they occurred at the same time. There is always a possible 4th return value, which would be the result of a comparison like this. In this case, the digit comparison between 6 and B would not return any relationship of earlier or later in a sequence. Similarly, consider this ambiguous question. We might speculate that any algorithm can return null or not return at all, which would be a catch-all whenever it cannot return a meaningful result and so cannot add a relationship. What's important here? You learned this algorithm. It cannot possibly be innate because before about 1,000 years ago, nobody knew this algorithm. Decimal numbers hadn't been invented yet. At some point, this mental algorithm was invented, and it has been passed down from person to person ever since. You know that 2 comes after 0 in a digit sequence, and you know the algorithm. A similar algorithm can be applied to alphabetization. Although computer sorts are numeric, human sorting is clearly based on order in a sequence. You didn't learn this algorithm with hundreds or thousands of repetitions the way you might learn language or playing the piano. Someone told you the algorithm and you implemented it. It took just a few times through the process to learn it. Subsequent practice makes you more proficient, but only a few examples are needed. From a computing perspective, this algorithm uses a number of CPU-like instructions, like the function call and return and a goto and the ability to check for a condition. Unlike a CPU, the conditions to check for are the existence of a relationship, and the action is to create a relationship between two given things. We could build a CPU with these capabilities, but we haven't yet. In short, neither neural networks nor large language models are intended to learn algorithms, especially from the small explanations and examples people learn from. If they could, it would dramatically extend machine intelligence. So the next time you answer any question, consider that your brain doesn't just know, it's often running beautifully complex internal patterns. Interested in pushing AI capabilities closer to human level? Let's continue the conversation. Share your thoughts in the comments, subscribe for deep dives into AI and cognitive models, and let's collaborate on building the next generation of intelligent systems by joining the Future AI Society. And as always, thanks for watching.